Stephen Chenoweth. I'm a marketing manager here in Intel's Technical Computing Group. Welcome to the Intel Discover Your Parallel Universe booth. A couple of the highlights we have at our booth today. So our marquee demo here, we're showing some ray tracing visualizations from the Texas Advanced Computing Center. These visualizations were created on Stampede, and Stampede is a Xeon processor and Xeon Phi coprocessor based supercomputer at the Texas Advanced Computing Center down in Austin. And so we have some medical research visualizations we're showing here. These were developed using ray tracing technology with a technology called Embry, and these were all visualizations were all based on Xeon processor CPU technology-based visualization. What these visualizations are running on is the first top 500 supercomputer to be shown on a conference floor. So this is the Cherry Creek system, scored number 400 on the top 500 supercomputers, checking in at a little over 131 teraflops of performance. So what's inside here? So every one of these nodes has two Intel Xeon processor E5 2600 V2 processors, and then three Intel Xeon Phi coprocessor 7120Ps. These are all interconnected with Intel TrueScale Fabric, and these also contain Intel solid-state drives in each one of the nodes as well.
You don't need to have big data in order to be concerned with supercomputing resources or high-performance computing. So right here, what we're dealing with are actually little data, we like to say, but big analytics. So we have air quality sensors that we've distributed around a neighborhood, and we've been working with people in the neighborhood to see what kinds of services they'd be interested in having. One of those things that they've talked about is they would really like to be able to plan a route as they run through the community. And we realized that what that meant was that we needed to have multiple sensors and do good interpolation. The neighborhood that we're working in is this one here. And so you can see these are the sites for the sensors right now. We've got a few more that we're going to be putting out. But what we want to be able to do is to figure out all these different streets, and that requires interpolation. And so what we did was we built a heat map. But then we realized that the heat map really wasn't going to be enough. That was after working on it for about a month, somebody asked us if we wanted LiDAR data to tell us where the buildings were and how high they were. And we said, yeah, that'd be great, we'll put that in. And once we did that, we realized that this model was broken. And here's an example of what we mean. So if we have a point source here, this is a simulation of how particulate matter would move through the community. You can see that this is a school right here. This playground is bad. This one's pretty good. The streets up here are actually much worse than this street, or this one, which is closest to the point source. So when we do this, we actually have to include a hypothesized point source, the flow models, and then we need to actually compare across the 12 potential sites of emission to do it. So to get a very simple solution like this, we actually have to use very powerful analytics.
Hi, my name is Keith Brewster. I'm a senior scientist at the Center for Analysis and Prediction of Storms at the University of Oklahoma, and I'm here at the Supercomputing Conference to show what we're doing with our supercomputer cluster, which consists of several hundred of the Sandy Bridge systems. And one thing we're doing is in real time, we are forecasting hurricanes and typhoons. This is an example from just last week where we were forecasting the hurricane that struck the Philippine Islands. And you can see the observed track here overlaid with our forecast. And you can see that it did a fairly good job here on the 5-day forecast. Just like the previous video, I'm showing where the track of the actual observed damage was from the tornado. In this case, there were two tornadoes here, third and a fourth. So as we go forward in time, this already is the model is spun up, and 17 minutes into that, we're showing the beginning of the rotation developing, and you'll see that going forward, following pretty closely to the observed track. And then as we go further, it shows redevelopment up to the northeast that is associated with the damage observed here. So this is what we're capable of doing today, but we would like to observe and forecast the tornado itself, which would require a much higher resolution. This is a resolution of 50 meters in research mode, not in real time, where we're showing the development of a tornado that was actually depicted here in the radar image. So we can see with time all of the dynamics that go into development of the tornado and compare it to the radar. Now the radar is only every 5 minutes, so it looks jumpy. It's not really telling us all of the detail that's going on when we have this continuous simulation as we have here. And of course we have the complete four-dimensional data set that goes with this. So we have pressure, temperature, wind. We can analyze all of the dynamics to understand better how tornadoes form. But ultimately, if we had a parallel universe with even more processors, we would like to do something close to this in real time.
We have two teams going head to head. They have to answer 15 trivia questions related to parallel programming and the conference and programming in general. And then we take them to a round where they're giving code. Now in the code that we give them, it was parallel code, and I stripped out the parallelism from it. And they're given 10 minutes to see how much of it they can add back in. And whoever gets the greatest speed up wins that portion of the match. We started with 8 teams in the Parallel Universe competition, and we've got a bracket system, and we will eventually end up with one winner. We've been having a lot of fun so far, seeing them show their knowledge of parallel programming and their skills in programming. When we have a winner, we will donate $25,000 in their name to Philippines Relief Fund.
Thank you for coming by the Intel booth today. We hope you enjoyed it. You saw some great demonstrations of the discoveries and innovations that can happen when you go parallel. So we hope you come back and visit us next year. We'll see you at SC13. Bye-bye.